My dear students, in this video, I am going to introduce Scalar Triple Product and its geometrical interpretation. First, I am going to define what is Scalar Triple Product. For a given set of three vectors A, B and C, A cross B dot C is called Scalar Triple Product of three vectors A, B and C. Scalar triple product of three vectors A, B and C is A cross B dot C. A cross B dot C. This is called scalar triple product of vectors A, B and C. The dot product is commutative, you know. Therefore, the dot and cross can be interchanged. You can write it as A dot B cross C. A cross B dot C, it can also be expressed as A dot B cross C. Dot and cross can be interchanged. So A dot B cross C is equal to A cross B dot C. It can be defined like this. Both are equal. So A, B, C. These three vectors A, B, C, A vector, B vector, C vector form a coplanar vector. The given set of three coplanar vectors. The three vectors are in the same plane. That's why they are called coplanar vectors. So A cross B dot C or A dot B cross C is defined as scalar triple product. Okay? Now we have to find out the geometrical interpretation of scalar triple product. You consider the vector A, B and C as a coplanar vectors. You consider the three vectors A, B and C. Let the vectors A, B and C are coplanar. Coplanar vectors. They are determined in a same plane. Defined by the origin, with respect to the origin O, OA is vector A, OB is vector B, and OC is vector C. OA vector A, OB vector B, and OC is vector C. Having these three vectors A, B, and C as coterminous edges of a parallelepiped, complete a parallelepiped. This is a parallelepiped having A, B, C with the coterminous edges of the parallelepiped. So complete a parallelepiped with the vectors with A vector, B vector and C vector as its coterminous edges. Coterminous edges of the parallelepiped. You complete a parallelepiped having A vector, B vector, C vector as its coterminous edges of the parallelepiped. OA is vector A and OB is vector B and OC is vector C. And A cross B is the vector acting perpendicular to both the vectors A and B. A cross B and A cross B acting perpendicular to the vectors perpendicular to the vectors A and B in the same plane. Perpendicular to the vectors A and B. And theta is the angle between the vectors A cross B and C. Theta is the angle between the vectors A cross B acting perpendicular to both A and B. And theta is the angle between the vectors and theta is the angle between A cross B and the vector C. Now, what is A cross B dot C? The scalar geometrical meaning of scalar triple product means we have to find out A cross B dot C. For that, by definition, A cross B dot C is equal to modulus of A cross B into modulus of C into angle between cos of the angle between A cross B and C. Theta is the angle between the vectors A cross B and C. Therefore, A cross B dot C is mod of A cross B into mod of C into cosine of the angle between A cross B and C, that is cos theta. Okay? Mod of A cross B into mod C into angle between A cross B and C is theta. Therefore, A cross B dot C is mod A cross B mod C into cos theta. Okay? See, A cross B dot C, by definition of dot product, A cross B dot C is modulus of A cross B into modulus of C into the angle between the cosine value of A cross B and C. That is, theta is the angle between A cross B and C, therefore cos theta. Mod A cross B into mod C into cos theta is A cross B dot C. Mod A cross B is, see, A cross B is the base area of the parallelepiped. See, A cross B, mod of A cross B is the base area. Base area of the parallelepiped. Base area. Base area of the parallelepiped into mod C cos theta. Mod C cos theta is height of the parallelepiped. Mod C cos theta, this is adjacent side of theta. OC is the hypotenuse. So this is right angle. So mod C cos theta is adjacent side of the triangle. OC is hypotenuse. So height of the parallelepiped. Base area into, see, mod of A cross B is base area of the parallelepiped and mod C cos theta is height of the parallelepiped. So you know, base area in height is volume of the parallelepiped. Volume of the base area in height is volume of the parallelepiped. So A cross B dot C, the geometrical meaning of A cross B dot C is volume of the parallelepiped having A vector, B vector, C vector as coterminous edges of the parallelepiped. So A cross B dot C is volume of the parallelepiped having A vector, B vector and C vector has its coterminous edges. Has its coterminous edges of the parallelepiped. Coterminous edges. So, geometrical meaning of scalar triple product is nothing but the volume of the parallelepiped having A vector, B vector and C vector as the coterminous edges of the parallelepiped. That's all about the geometrical interpretation. Now, we have to see the properties of scalar triple product. Our next idea is, we have to see the properties of scalar product one by one. You know, A, B, C are coplanar vectors. A vector, B vector and C vector are coplanar vectors with respect to the origin O, OA, OB, OC are the position vectors of A, B and C, the point. A, B, C are coplanar vectors. See, its property, you know, the scalar triple product of these three vectors is first property A cross B dot C. Okay, A cross B dot C is the scalar triple product of the three coplanar vectors A, B and C. See, you consider cyclically A, B, C, B, C, A, C, A, B. Like that you will consider. A cross B dot C, then B cross C dot A, then B cross C dot A cross B dot C, and B cross C dot A, and C cross A dot B. You consider cyclically the three products, scalar triple products, A cross B dot C, and B cross C dot A, and C cross A dot B. They are equal. These three are equal. If you consider cyclically, okay, cyclic order. If you consider in cyclic order, they are equal. A cross B dot C equal to B cross C dot A equal to C cross A dot B. These three are equal if you consider these in cyclic order. And these scalar triple product can also be expressed as box product. This is expressed as in square bracket you write it as ABC, and this is called box product ABC. Box product ABC. This is equal to box product BCA. This is equal to box product CAB. In the square bracket notation you have to write, and this is called box product. Okay? Scalar triple product is otherwise called box product ABC, BCA and CAB. And this is the first property. If you consider in cyclic order, they are equal. If you interchange the order, the sign of the box product is vary. Suppose A cross B dot C, if you write it as B cross A dot C. See, this is changing the cross product in A cross B. If you change the B cross A, it should be equal to minus of A cross B. Sorry, minus of A cross B dot C. The sign of the box product is changed if you interchange the or otherwise this is box BAC minus box BAC equal to box ABC. If you can write it also. If you interchange the order AB instead of BA, the sign of the box product is changed. Either you have to write the sign here or here, whatever it means. Anyone, if you interchange the sign of the box product, order of the box product, the sign will be changed. Similarly, instead of BCA, if you write CBA, BCA, box product ABC, instead of here, you can write it as you write box product ABC. If you change the order BAC, it becomes negative. Similarly, BCA is or ABC, BCA, if you change the order of CBA, if you change the order, then negative box product becomes negative box product will get. Sign of the box product is changed. Similarly, CAB, if you change the ACB, sign will be changed. So this is a property. So first one, this is second one. If the order is changed, the sign will be changed. Okay. So instead of cyclic order, if the order is changed, sign of the box product will be changed. Okay, that is the next property. And if the two in the box product, if any two vectors are equal, if any two vectors, third property, if any two vectors are equal, say AAB. Box AAB. Two vectors AB instead of B. C vector is also AAB. In this case, you can write it as A cross A dot B. You know A cross A is 0 vector. A cross A is 0. 0 dot B is 0. So if it is 0. If any two vectors are equal, their box product is 0. That is property 3. Similarly, one more example. If CAC, you consider the case, in the box product, two vectors are equal, CAC, it's also the value of the box product is 0. Like that, if any two vectors are equal in the box product or scalar product, scalar triple product, if any two vectors are equal, then the value of the box product is 0. That is property 3. Okay? Then fourth property, if lambda is any scalar, then lambda A cross B dot C. The box product scalar triple product lambda A cross B dot C. The scalar lambda can be multiplied with any one of the vector A, B, C. It is, you can take that lambda scalar out of that product A cross B dot C. Like that you can write. So this is lambda A, B, C is equal to lambda times of box product A, B, C. So inside the box product, if you find any one of the vector is multiplied by a scalar, then that scalar can be taken out of the box product. Lambda times of A cross B dot C or lambda box product A, B, C. The scalar can be taken out of the product. That is property 4. Fifth one. The scalar triple product of any three vectors is 0. The scalar triple product of any three vectors if the scalar triple product of any three vectors is 0, then the two vectors are parallel or collinear. Then any two vectors are out of the three vectors, then any two vectors in the product, the scalar triple product of any three vectors is 0, then out of the three vectors any two vectors are, any two of them are parallel or collinear. If the box product of any three vectors is 0, then out of them any two are parallel or collinear. This is property 5. Sixth one. If the three vectors A, B, C are coplanar, if the three vectors A, B, C are coplanar, then if and only if the three vectors A, B, C are coplanar, if and only if the box product A, B, C is 0. So A, B, C, it can be expressed as A, B, C vectors are coplanar is true and if and only if the box product A, B, C is 0. If the three vectors are coplanar, that box product is 0. If that box product is 0, the three vectors are coplanar. Two-way inlet. This is property 6. Okay? See, as a note I can say, if the scalar triple product of three vectors A cross B dot C is 0, then the conditions are 1. The scalar triple product of any three vectors is 0, then any two of them are parallel or collinear. second condition, the three vectors A, B, C are coplanar, then the box product is 0. See, if the box product A, B, C is 0, any two vectors are coplanar, or then any two vectors are parallel or collinear. And second condition is the three vectors are coplanar. And the third condition is the volume of the parallelepiped is 0. The volume of the parallelepiped is 0. These are the three conditions we can infer from the box product ABC is 0. If box product ABC is 0, any two of them are collinear or parallel, and the three vectors are coplanar, and the volume of the parallelepiped is 0. These are the three conditions are inferred from this. If the box product ABC or A cross B dot C is 0, we can find that any two of them are parallel or collinear, and the three vectors are coplanar, and the volume of the parallelepiped is 0. Those are the conditions we can infer. So that's all about this video, and we will continue in the next video. Thank you.